Okay, great. So let's start. Today we are talking about again transformer model mostly, and so previously last time we discussed we discussed the disadvantages of previous approach, recurrent neural network architectures. Then we switched to attention mechanism and discussed the uh, theoretical parts of transformer architecture, mostly in slides, but today we are trying to implement everything in Python. So to dive into all the details and actually to build a generative pre-trained transformer or GPT version 2. So it is possible. It is not GPT-3 or even GPT-4, which of course way more bigger. So we can actually implement and even train GPT-2 at the moment. So let's do it. So the first step is let's recall the underlying structure of transformer model. So this is the picture from Attention is All You Need paper, and I hope that now you are a little bit more familiar with the two parts of this architecture. So the first is encoder block here, and we actually perform self-attention inside this block. So this is multi-head attention block. The main part of it then goes feed forward, neural network at the top of attention, and then we repeat this this block usually 6 times or more, and this way we are getting new representation of input words. Actually, we are starting with some words, then we embed them to vectors, and then we get so-called contextual embeddings, which gather all the information about, for example, sentence, if we want to translate sentence from one language to another. And you see here these arrows, so the contextual embeddings of our input go to the decoder block, to the actually middle point of this decoder block, again on the multi-head attention block. So here it is self-attention, and then in decoder we have a very similar scheme of operations. So we start with multi-head self-attention, and it is masked because we don't want to look into the future. We hide future tokens because usually we want to predict next token, next word, and this is our task. So we cannot show the right answer to the model. That's why here we use masked multi-head attention, and then goes cross attention or classical attention block between the contextual embeddings from decoder and all the contextual embeddings from encoder, so from the input. And the result is actually, if we want to translate one sentence to another, then we get sentence in other language. Yes, so here is actually we are solving the familiar classification task, because we want to predict next word or next token. It's almost the same, and we have vocabulary of all the tokens, so we need to specify, to choose to predict ground truth token based on all the model here and based on our input and the prefix of output. So some prefix tokens. Okay, and now we are importing Torch, of course, because we will implement everything in PyTorch. And the first step is downloading the input txt file, which has all the data set we want to use to train the model. again, the same as we've done in recurrent neural network models, we need data set to train, so to perform training of the model. And here you see the length of data set is in characters. So again, here we will try to train GPT-2 model on characters level. So because it is easier, so for simplicity. And the length of data set in characters in all the letters is, you see, about 160,000 characters, and we can read the first about 100 letters, and you see this is some book about St. Petersburg mathematicians and their discoveries. So firstly, we of course need to encode all the characters on the base level, and that's why we are creating, as usual actually, the vocabulary with all the characters inside this data set. So you see a lot of capital letters, so all the alphabetic letters from English alphabet. Here is because the book is in English. Here is lowercase characters, and then some special signs, some strange signs, Russian and Greek letters also. So this is, you see, some mathematical signs here, because it is input txt format, so we simply join all the unique characters from the text. And the size of vocabulary for us is 173. Let's remember this number. It is important. It is the amount of classes we want to predict on the top of our model. And the next operation is creation a map. So in Python it is dictionary, so mapping from characters to integers. So we want to be able to encode all the characters to their indices, and vice versa. So index to string or index to char, to character, is reverse mapping. So they are they're going together, and here is two very simple operations. So the encode operation, which gives us all the characters according to the, so take a string and output a list of integers according to the numbers of characters in our mapping. And on contrary, decode operation, decode function, take a list of integers, so the codes of characters, and output the string corresponding to these numbers. So for example, if we encode hi there phrase, then you see numbers of the letters from the our vocabulary. So for example, you see here HII and number 66, 67, 67. So this is the numbers of letters. Then goes 1, and we see space here, so the 1 is number of space in our vocabulary, and so on. And of course, if we decode encoding information, encoding numbers, then the result will be the same hi there as input. So it should be the same, So it works, and we can use encode and decode functions to perform transformation between characters and their indices, and vice versa. Then let's go on. So all the text, we firstly encode it to numbers, and then we put all these numbers to PyTorch sensor. So here is the construction, and it is our data for the model. So the encoded characters of the whole data set. And of course, we see the same number of indices in the data, and the type of data is now integer 64, and the first 100 characters is looking like this. So we see some characters, then space, and again characters, space, and so on. So we can understand what is going on, and this is our base, so very simple encoding of the input information. So this is our data set for training data variable. And now, as usual in machine learning, we split data to two parts. So this is training data, the first 90% of whole data, and then the rest is validation data to compute some metrics to understand what is the quality of the model. Yeah. And now let's go to the building of pairs, object and answers. So of course we want to train the model in supervised way. So we need to create sequences. So here you see X and Y. Yeah, and actually, as we've done previously in recurrent neural networks, again the X data is sequences of block size. So if block size is 8, so it is our context length here, then the input is 8 numbers, or I hope you remember, or 8 letters. Yeah, and then the answers are simply the same sequences shifted to on the one to the right. Okay, so for the first number 47, the answer, the target is 78 because it goes after the 47. Then for the first two numbers, the target is 11 because it is third number, and so on. Yeah, so for each prefix of these sequences, the last number is the answer, and then we go to the you see to the pre-final number 63, and the target is the last number. Target is 76. So based on one sequences, we create eight pairs of objects and answers for these objects. And so it means that here we want to predict next character based on the no more than 8 characters in the window. Yeah. So of course for the whole data set and for the generation part, we will almost always use 8 numbers to predict the next one. But for the training purpose, we should show the model the beginning of the sequences. So here, that's why we use so different numbers of input tokens. So here, this is a number of our tokens. The tokens for us will be simply characters of the elements of vocabulary. And now we go on. So together with block size, which will be 8 for us, we should specify the batch size. So the batch size is the number of independent sequences which we will process in parallel. Yeah, so we can count all the losses for so independently for all the elements in batch. And here we will use 4, again just for simplicity. So our batch, our input for the model will be, so here you see it, will be 4 objects, and each object is the sequence of 8 numbers. And of course, for each sequences, we have this procedure of creating context and target pairs. Okay, so context is object and target is next character for this sequence. So, and here you see the result, all the X in batch and Y in batch. And if we start with 4 parts, 4 elements in batch, then the targets should be this one. Yes, because again we predict next, each time we predict next character based on the first one. So here you see for 62, yeah, the next token is 1. That's why the target in tensor here is 1. Then for first two numbers, 62 and 1, the target will be 64 because it is the next token for this sequence. Okay, and that's it. So based on data set, we can cut it on the sequences and construct batches for the model. So this is our input to a transformer model. So you see, essentially, the now the shape of X batch is two-dimensional tensor with 4 rows and 8 columns. Okay. And now, so based on these input, we are ready to implement basic. It is not transformer model. It is the again bigram language model as we used before. And in bigram language model, we just predict the vector of lookup size with all the row scores and then probabilities of next tokens. Yeah, so we actually take the number, so here is numbers of characters, and again the maximum number is vocab size, and it means that we simply select the row from one trainable layer in the model, and this is this neural network embedding layer, which is essentially simply linear layer, so the two-dimensional matrix of weights with these sizes, this form, so lookup size by lookup size. And that's why for each input token, we can simply select the row of this layer, and this row gives us row scores for next token prediction. And then, so here you see the forward method, we simply take logits as row from embedding table, and then we use them to predict, so to softmax everything and to predict probabilities. So here you see cross entropy. It means that logits inside cross entropy, they will be normalized. So the functions inside cross entropy is firstly softmax. It gives us probabilities of the next tokens, and we have targets, and targets means simply ground truth answers. Yeah. So here I need to correct. We have 173. Yeah. So 173 tokens in the model, and here is so we use logits to predict probabilities, and then we take logarithm of probabilities to calculate the loss according objects in certain batch. Okay, and the result of forward pass is so the vectors of logits, this one, and the value of loss function to use these loss function for backpropagation step. Yes, for calculating gradients and updating all the parameters. Yeah, and here near the forward pass, we should implement the generate method, because we want not only train our model, but we want to inference. We want to predict, to be able to predict next tokens. And if you look into the code, you will see exactly the same operations. So for each new sequence, so we simply and again in background model we are using only the number of previous token to predict next one. Yeah, so that's why we here apply our model, so self of number of current token, and it gives us the logits and loss, and then we take only you see here -1, so we take only last element of this logits tensor. Yeah, that's why it becomes batch size on the channel size, and channel size is 173. So it means that for each element in batch we predict the vector of logits, and then based on this vector of logits we calculate probabilities. So for each object we calculated the probabilities of next token, and then we use these probabilities to perform sampling. So here is Torch multinomial distribution. It means that we use these probabilities as probabilities for tossing a big coin with 173 variants, yeah, of answer. And the actual answer is next index. So we simply add, when Torch concatenates, so we add new index to the output and return this output. Okay, so to repeat this loop actually. So for range max new tokens, we generate them character by character. Yeah, based on the previous, we generate next one. And of course it works, so we can print generated sequences after decoding, and of course without any training. So here you see results. Without any training, the batch size for us here, let me show, is batch size is 32. Yeah, so this is the logit shape, 32 by 173, and the result is some random characters. So you see here 100, yeah, about 100 random characters, because we don't train this model, but we can train it and get some results. Let's do it. Yeah, so and what is our expectation about general loss, about average loss? So what do we need to improve in our model? So imagine that instead of this bigram model, we have only uniform distribution. So we simply, each time we simply sample one character out of 173, so out of our vocabulary, yeah, of all the variants. And then the cross entropy for such random model, yeah, very simple, will be essentially the logarithm of probability for each character. And the probability of each character is the same, is 1 divided over 173. Yeah? That's why the average loss for this random model will be minus logarithm of this probability. And this is the number, yeah, so 5.1 and so on. So this is the evaluation average loss for very simple random model. So of course our trained model should be better. Yeah, so we want to decrease these numbers, so we want to get better loss and to predict something, even based on one character, but we want to use the data set to train better model. And again, so to perform weight updations, we need to specify optimizer. As usual, we can choose either stochastic gradient descent, SGD, or some versions of other optimizers. So here we use weighted Adam, and Adam is adaptive momentum optimizer. So we simply state here that we want to optimize all the parameters of the model, and the model is bigram model with some learning rate. Okay, and then we actually perform training. So batch size 32, and firstly we get batch from train dataset. Then we perform forward pass of a model. We here zero gradients and perform backward step to calculate gradients based on the current loss. And optimizer step updates all the parameters in the model. So here for bigram simple model we have only one two-dimensional tensor of parameters. And then we train it. You see here 50,000 steps, but the model is very simple. It has actually not so many parameters. This is all the parameters, yes, all lookup size squared. And but the result, let's wait for, I don't know, for 10 seconds to see the final loss. Okay, so after all the optimization, we get, you see, twice better loss than for random model. So it trains and it works. So even for this very simple model, we can generate new text similar to the train. And here you see spaces, then commas, so the model, and it tries to put new lines, yeah, so some words we can even read, so or just, and so on. So the result is much better than random model. And of course, if we increase the number of steps, we will get better results. But if you remember, this model, bigram model, is almost the same as statistical model of calculating the numbers, all the numbers of bigrams based on given data set. Yeah, and of course we need, we want more. We want to change our model to transformer, and then to train it and to perform generation based on the transformer model. So let's do it. And before we go into details of transformer and attention mechanism, let's start with very simple mathematical trick in Python. So our goal now is to somehow to aggregate all the embeddings from the input. So suppose our input has this shape, so 4 by 8 by 2. It means that suppose we have 4 objects in batch, so this is batch size, and each object has 8 characters inside. Okay, so 4 by 8 characters overall, and each character is represented not with one number as previously, but with two numbers. Okay, so here C is our embedding matrix, and suppose it has the so C equals 2. Yeah, so the input size, input shape of our tensor is 4 by 8 by 2. This is the size of embedding. It could be different. So instead of 2, we can use 10, 100, and so on. But 2 is convenient for demonstration and for visualization. So let's take 2 as new size of embedding. Yeah, and then so our input without any operations, yeah, is so this is our input x0, so the x is all the objects, and x is the first object in batch. And you see the first object is batch is 8 vectors with size 2 each. Okay, so 16 numbers in total, but each vector here is embedding of some character from the input. Okay, so this is the first object in batch, and you see 8 rows here. Each row represents one character in the input tensor. And so our goal, if you remember the attention mechanism, our goal is to force these vectors communicate each other, so to change the information. And one of the simplest way to do it is simply averaging. So here we perform torch mean operation for averaging of the vectors along the second dimension, so along by the columns, yeah. And you see, so x bow, so bow here means bag of words. So we simply averaging the components from the first to not to the last, but we average prefixes of these tensor. So you see the first vector is not changing. This is 1.9, 1.4, and this is the same numbers. But then the second vector is different. So you've seen here 0.9 and minus 2.1. And here, what is it? It's simply the mean, so the average of first two components divided over 2, because we add 1.9 and 0.9, and then divided by 2, and the result is 1.4, about 1.4. And the same for the second component. So 1.4 plus minus 2.1, it is about 0.7, yeah, and then we divide it on the 2, so the result is minus 0.3, and so on. So the third vector here in xbow is the mean components of first 3 vectors in the original data set. Okay, and to do it here, we simply first, this is the first variant, the simplest way. So we perform two fors in Python. Okay, so for each element in batch and for each number of character t, we take first t components and then we average them. Okay, so torch mean of xpref. Now we want, so our goal is the same. We want to perform averaging between components, but we want to do it different way, more effectively in Python actually. So, and this is the first different approach. If we build in Python, in PyTorch, there is trill matrix and trill operation. Yes, so for matrix consisted of ones with shape 3 by 3, we trill it. It means triangle low. So you see it becomes low triangle matrix. So the non-zero elements are only on main diagonal and low the main diagonal. So this is trill operation in PyTorch. And using this matrix, we already can perform almost the same operation as before, so averaging of components of input vectors with matrix multiplication. So this is our first trick. Instead of using loops in Python, we simply perform matrix multiplication. Yeah, and let's look at the result. So our A matrix is low triangle with ones inside. Our B matrix, for example, is input tensor of 3 vectors with 2 components each. And then we perform matrix multiplication of 1 and B. Yeah? So we multiply first row of the matrix on the first column of matrix B, then we multiply first row on the second column, and then we go further to the second row of the matrix A. Yeah? And the result, of course, is clear. So the first operation is not changing first row. It is 2, 7, 2, 7. Yeah? Then the second operation simply adds first 2 components. So 2 plus 6 is 8, and 7 plus 4 is 11. And then the third operation is sum of all the components along the dimension, along the columns. Yeah? So it is almost averaging, but to perform averaging, we simply need, so this is the second step in our mathematical trick, we simply need to normalize the low triangle matrix consisted of ones. Yeah? And this is it. So here we add one line, we divide the original matrix on the sum inside each row. Yeah, and the result is matrix of weights. So the first row is binary vector. Then the second is the second has only 0.5 in 2 first places, and so on. So this is the weights for averaging. So if we multiply our input with size 8 by C to this matrix 8 by 8, then the result will be exactly X bow. So the second variant of calculating X bow coincides with the first one. Yeah? So we replace 2 cycles with 1 matrix multiplication. Okay, and of course it works for any dimension. So we need to specify T, so the amount of tokens inside sequence, and then perform this operation to get the same averaging as previously. But it is not the end. Yeah, so the next step is again doing the same, but with third way. And we again starting with lower triangle matrix, but then instead of matrix multiplication, we want to use softmax operation, from PyTorch. And actually, so here we create triangle matrix, then 0 matrix T by T, then we fill all the upper elements from the 0 matrix with minus infinity elements, and perform softmax with this new matrix of weights. Let me show you the results. Yes, so the low triangle matrix is this one. It is binary with ones and zeros. And then after replacement, so the matrix of weight here consists of 0 and minus infinity in each row. And let's think about what if we softmax each row of this matrix. Yeah. So remember, the softmax is firstly exponential of each exponent of each component, and then we should divide each component on the sum of all the results. So of course the exponent of 0 is 1, the exponent of minus infinity is 0. That's why we divide first row on 1, second row on 2, because of sum, so sum of 2 ones. Then the third row on 3, and so on. So the result of softmax for these metrics will be exactly these metrics, okay, with specified weights we want to use. And actually that's it. So our XBOW third version again is the same as the original expo result. Okay, so all those, they are perfectly coincide. And of course, in attention mechanism, so this is our final result, we will use almost the same procedure, but with different weights. So here we have no any parameters, we simply average input embeddings with some weights. Yeah, and our goal is now to replace these weight metrics to trainable and to include attention layer inside this operation. So we already have the input, we know what is the shape of output, and the last step is to include trainable attention or some other layer inside, so between these two states, between input and output. So let's do it. This is so this is the same background language model with but let me show you here the attention mechanism. That's it. So this is fourth and the last version, self-attention, which we will train. The input is almost the same. So we again we have 4 elements in batch, 8 characters inside in each element, and here c equals 32. It may be again 2. It's not very important, but here is the real dimensions. So the length of embedding for this attention layer will be 32. We can change it to other dimension, but here let's work with 32. Then we introduce attention layer, and inside attention layer we use 3 trainable matrices. Yeah. So what is trainable matrices in attention layer? Actually, we perform linear operations, so linear layers inside, and the first dimension is C, so the amount of components in the input, and the second dimension is head size, so our resulting dimension. So this is the D from on slides in the previous lecture, and D is the size of projection space. So actually we project X's, so this is our input, X's the tensor, 3-dimensional tensor with all the characters, yeah, and their embeddings. And we project it, so C project to 16 to the head size. Okay, so this is the result, the shape of result, B times T times 16, and we get 2 new tensors, the key, K for the keys and Q for queries. Yeah, and then here is the attention formula. So we simply multiply Q with K transpose. Okay, so with K transpose, so actually it means we change -2 and -1 columns, so to get these the corresponding shapes. Yeah, so our goal actually to perform, if you remember, dot product of K and queries, so for all pairs of queries and Ks. And so the really simple way to do it is again matrix multiplication. So B is the same here, left dimension, and T by 16 and 16 by T gives us the T by T shape of the result. Okay, so here we get rid of head size, and this is our weight matrix. Actually, this is the same weight matrix as we've built here, so for multiplication on the input tensor X. But here it is already trainable. Yeah, so it has at least key and query parameters inside. And then we use low triangle matrix to hide all the tokens from the future. yeah, and then we softmax results. So again, to get the attention scores. So here is the original value of matrix is raw scores for the attention mechanism, and after softmax it will sum up to 1 along all the rows. So the result here is matrix of attention scores, which we should use to get the output. And essentially the output is matrix multiplication of weights and x's, but here we introduce third linear layer of attention mechanism, and this is value layer. So you see here we use again the linear layer which project C to head size vector, and then we multiply matrix of weights with values, and this is the output of attention head. This is one head in attention, and of course the shape of output will be B, which is 8 by T, amount of tokens, by 16, which is head size. Okay, because we project X from 32 to 16 and then perform the matrix multiplication. Okay, so maybe if you have any questions here, please ask, because here we discussed all the details, how to perform attention layer in PyTorch, and now so the next step is to gather everything in one cell and then to train model, actually to train transformer model. Now we are ready to do it. Okay, so some notes about attention is some communication mechanism between token embeddings, and just inside an attention there is no notion space. So that's why we need to add positional encodings to these token representations. And we can proceed all the elements inside, so across batch dimension independently in parallel. And so it was the example with triangle lower mask for decoder step, and in encoder step we have no masking, because we all the tokens from the encoder, from the input, should communicate each other, so to enrich each other with information, with to get contextual embeddings. And so the last step is division of weights to the square root of head size to preserve unit variance inside attention mechanism. And this is the illustration. If we divide the result on, you see, on the head size, on the square root of head size, then the variance of, so if the variance of k is about 1, variance of q is about 1, then the variance of resultant matrix will be again near the 1. And if we comment this term, then again, so the original variance they are about 1s, and the result here is 16. So much worse. So we want to preserve variance. That's why we divide the result of matrix multiplication to the square root of head size. Okay, and now we're ready to combine everything. Yeah, so this is the PyTorch head attention class, and it has three layers with parameters, which projects all the embeddings to the space with head size dimension. And here we create these masking metrics for attention in decoder. Yeah. So here we won't use dropout. It simply will be 0. So it's not important for the for now for attention mechanism. And this is forward pass. So based it is the same we discussed earlier. So based on the linear layers of key, query, and then in the end of value, we perform forward pass for attention head, and it means that we take X with shape BTC and return the result out with shape, actually with the same shape, yeah. So BTC in this, in this situation. Okay, so so head size, it is value is not BTC, yes, so value is X is BTC, and value of course is BT head size as key and queries. Okay, and then after performing this operation, the result will be again BT head size. Okay, that's right. So let's go on to the whole model. The model is has all the same hyperparameters. The batch size, it was 4, but now we changed to 16. Then block size, it was 8, and now it is 32. Then the maximum iterations, the evaluation interval, the learning rate, device to perform computations, and so on. So here you see the embedding dimension, yeah, so 64 instead of 2 or 32 or so on. Yes, 64. This is the final embedding dimension for the transformer model. Then number of heads. So n head is number of heads, and then number and layer is the number of blocks in decoder. Yeah, so maybe you remember the big N, yeah, number of transformer blocks, or big N in our slides. Okay, and this is for this transformer model. So let's look into the classes. Yeah, so we specify all the hyperparameters for the model. Then we create, here again we read the data set, we create simple encode and decode operations just to convert characters to numbers. Yeah, this is the same splitting to train and val or test. Yeah, so data sets the same get batch function, and the usual estimate loss. So when we want to print loss, we need to take batch and then to calculate loss. And this is, you see, the model evaluation mode. It means that we simply use model for so we don't calculate gradients here in evaluation mode. So we just apply model to the batch and then write losses, yeah, here. And then we switch the mode to train mode back, so to return to training. And let's go on. So this is the same head class for attention model we just discussed, yeah. And here we need to change. Let me do it. The head size. Okay, head size for value. Okay, head size for value. This is it. Great. Then so that's why you see, we actually change the size of embedding. It was, let's say, 64, yeah, it was 64, and then the head size is 16. So to return the 64 size for dimension, here you see it, we need to implement head for range num heads. So num heads for us is 4, and then here we will get, you see, we will get 4 heads with 16 head size in each, yeah. So it will be 64 elements back after the multi-head attention block. So we return 64 dimension as it was originally, yeah. So we see 64 and we save the same dimension because we again want to stack these transformer blocks, yeah. That's why we need to have one and the same dimension in the end and in the beginning of each block. And here is, you see, the concatenation step. So we firstly we calculate all the heads, and then we perform, so we calculate vectors and concatenate them just one by one. Yeah, so first result of first head, of second, of third, and the fourth. And that's why the output will have 64 dimension, 64 size. And it is almost it, yeah. So here is the feed-forward block, which consists of 2 linear layers, as we've seen in slides before. So one linear layer, activation function, second linear layer, and again dropout is 0, so we can simply comment it. It is not important for now. Then we put together the multi-head attention and feed forward in transformer block class, okay. And this is self-attention layer, so the whole multi-head attention with 4 heads and 16 as head size. And you see, actually, head size is so 64 divided over 4, yeah. So yeah, each head will have this size. So 64 divided over 4 is 16. Great. And then goes, so after self-attention goes the feed-forward layer. So actually this is the feed-forward block with 2 layers. Then goes layer normalization. So the first layer normalization and the second layer normalization. And the forward pass, so the applying of transformer block to the input, is the same as we've seen on the picture. So firstly we calculate self-attention after linear normalization of x, and then we add this result to the original x. Then we take this new x and again perform linear normalization to with feed-forward layer, and it is our result. So the result of transformer block is new contextual embeddings based on the original embeddings X. And the whole transformer model, of course, consists of these transformer blocks plus the token embedding table, position embedding table. They are the same, but you see the transform backup size to the number, to the dimension of embedding. And here the final linear layer is back transformation from embedding dimension to the VCAP size. So here the result of this last linear layer is, so linear model head is the logits, okay, so the raw scores which we are using in softmax for calculating probabilities, and probabilities are the answers of the model, okay. So, and you see here the forward pass, the logits is the last step in transformer model, and based on the logits we can calculate loss with cross entropy function, as usual in classification task. In general, that's it. So we need to, of course, perform to implement the generation function, but you see the generation function is just the same as before, but the only difference between pigram model and transformer model, that of course here we want to use more tokens as prefix. So we put into the model all the, I don't know, 8 or how much tokens we want to use here. This is it here, block size. So yeah, 32 characters, and based on them we predict next character. Okay, and here is the generate function. So we simply select 32 tokens, then we perform transformer model, and based on logits, actually on the last logits, we transform them to probabilities and sample next number of token, in our case character, based on these probabilities, and then we concatenate next token to the all the previous ones, and then we repeat the steps. So we move the window and predict next token, and so on. And this is transformer model, so-called autoregressive transformer model, autoregressive decoder. Here we have only decoder, as you see, and let's do it. So here, yeah, 2 minutes. Okay, let's do it. So I am running the cell, and you see the overall number of parameters inside this transformer model, and actually this is GPT-2. So you see it trains. The loss here is almost random loss, as we've seen for our vocabulary of 173 tokens, and then loss is decreasing, yeah, both on train set and on test data set. And yeah, so after, you see, in 1 minute we will have results from the model. So let's wait a little bit, and we can discuss layer normalization code during training process. So yeah, the layer normalization, the last layer in our model, is pretty simple. Yeah, so on contrary with batch norm, so this is the replacement of original batch norm layer. And you see here we want to change the mean and variance of the vector x, and here we simply, so the result is self out, and x hat is vector with standard, so with 0 mean and 1 as variance. You see we subtract mean value and divide it on the variance, so we normalize to unit variance, and then we multiply x hat with gamma and adding beta vectors, and both of them, so gamma is our new means, and beta is our new means, and gamma is our new variances. Okay, so we train them, they are trainable because of torch ones and torch zeros, and they are two vectors of parameters for layer normalization, layer actually. And so we train inside, so we put inside transformer along with all the attention parameters. We train new variances and new means for the model. So again, to be able to better predict next character. This is our ultimate goal. So great. Here is the train. Yeah. All the steps, so we perform 5,000 steps, and this is the result. So we generate text based on the book about mathematicians and their results, and you see here Bernoulli, we can almost read it, is there, that he is. So it is really much better than bigram model, and it is even very similar to the original text, but of course with some strangeness inside. But we simply take some text, yeah, and train the model for only 2 minutes, about 3 minutes, yeah. But the result for this setup is really amazing. So of course, if we train, if we increase the number of parameters and the time of training, then actually we will get first the GPT-3 and then GPT-4. As you see it, so the ChatGPT model is very smart, and it can answer different questions, but inside, so the general structure is the same as GPT-2. Still the same. Okay, so that's it for today. If you want, you can look at the structure of ChatGPT. Yeah, so from the blog post from OpenAI, and I think you will understand almost everything inside these actually popular blog post. Yeah, and this is what are the next steps after training some foundational model as GPT-3 or GPT-4. Yeah, and what we do next, so to get ChatGPT as a result. And yeah, and this is let me show you the very nice visualization of different GPTs. Yeah, so you see here large language models visualization. So we use almost not the GPT-2, yes, so it will be something similar to Nano GPT, but a little bit more. So here you see 85,000 of parameters, and we had 200,000 of parameters about, yeah. But all the blocks here, so they are, if we want to zoom in, so here are the attention blocks, and then goes multi-layer perceptron, so the feed-forward blocks, and then we repeat everything, and this is the structure of the model. This is last layer norm, and then logits, and then after applying softmax, it becomes probabilities, okay, to predict next characters. Then, so this is Nano GPT. The GPT-2, you see 124 millions, and then GPT-2 large variant, so you see 1.5 billion parameters here, and this is GPT-3. So you see, this is GPT-3. It is really huge, but the structure is the same. The structure is the same as GPT-2, but it has much more heads and dimensions and so on. Yeah, so you see on this visualization a lot, way more parameters than we had in GPT-2. Okay, so let's finish here. Let's stop here. Yeah, I wish you a Merry Christmas, Happy New Year, and hope to see you next semester, next year. Okay, have a nice evening, and we are preparing a New Year contest for you, but I will post all the information in 1 week. So after all the assignments, homeworks, you will be able to solve second contest. Second contest in machine learning. Okay, thank you for attention. Great, see you.
Thanks. Bye.